Okay, so we're going to do Lewis structures this year, but there's a little bit more depth to them. We'll start with some basic ones. H2O. H2O. So you have to start by counting the number of valence electrons that you have available to you. Oxygen brings 6, hydrogen brings 1, and there's 2 of them, for a total of 8. I want you to show this step. If you don't do this step, there's a good chance you're going to put the wrong number of electrons in your diagram. You blow the diagram, you blow the Vespa shape. So, alright, so the element with the highest combining capacity is usually the one in the center. The combining capacity for hydrogen is 1, can make 1 bond. Oxygen can make 2 bonds. So oxygen goes in the middle. Alright. You place the other 2 atoms and you put a bonding pair between them, and then you subtract that number from your total, and then you complete the octet around each of the atoms. So you can see that hydrogen currently is satisfied. It's got 2 each. Oxygen is not satisfied. Right now it only has 4 electrons. So those remaining 4 will go on oxygen as lone pairs. Some of you may have drawn it like this. That's okay. When we get into Vespa shape, you'll see why the top one is better. Okay, formal charges. This is an extra step. Formal charges. Formal charges help tell you which structure is correct. It's mostly used for polyatomic ions, but I'm going to show you how to do it using a simple structure. Okay. So we want the lowest possible combination for formal charges. So as many atoms as possible with a formal charge of 0. So the formal charge on oxygen, oops, sorry, it's supposed to be a colon. Alright, formal charge on oxygen. So you take the number of valence electrons, 6, you subtract it the number of lone electrons, so that's 4 total. 2 pairs is 4, minus the number of bonds. There's 2 bonds. So that gives us a formal charge of 0. We want zeros, so that's awesome. Hydrogen. 1 valence electrons, no electrons in lone pairs, 1 bond each for a total of 0. Now, because there's 2 hydrogens and they're identical, we would multiply this by 2. Right now, 2 times 0 is 0, so that's okay. The sum of your formal charges should add up to the charge on your compound or ion. So compounds are always 0, so 0 plus 0 plus 0 is 0, so this is awesome. So there's H2O. Let's do another one. Let's do ammonia. NH3. Nitrogen brings 5. Hydrogen brings 1, and there's 3 of them for a total of 8. So you put your central atom, the one with the highest combining capacity. Nitrogen has a combining capacity of 3 because it has 5 valence electrons and it wants 8. So hydrogen, 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 bond, bond, bond. So I've used 6. I have 2 left. They're going to go on to the nitrogen because hydrogen is satisfied, but nitrogen only has 6. There's 2 more to place. So they're going to go on nitrogen to complete its octet. All right, let's check if the structure is right. Nitrogen has a valence electrons of 5 valence electrons, minus 2 electrons in lone pairs, minus 3 bonds, gives us 0. There's hydrogen, 1 valence electron, no lone pairs, and 1 bond each. You do this for each atom, which is why we have to multiply your answer by 3. So this all adds up to 0, which is awesome. So that's how you do Lewis structures and formal charges. If you remember, I think last year we did TVS as well. TVS is really useful. And the reason TVS is really useful is because it can tell us how many bonds are in a structure. But it only works if you do not have an expanded octet, and we'll get to that in a minute. So TVS, total wanted. Now this has to do with completing an octet. So all atoms will be 8 except hydrogen is 2, boron is 6, everybody else is 8. Valence. This is V stands for valence electrons. How many does each atom bring? And then S is shared electrons. To get shared electrons, you subtract the S from the T. And that will give you a number. And if you divide that number by 2, it tells you how many bonds. So let's do COH2. These elements are all on the second row, except for hydrogen, which is on the first. So we know there's not an expanded octet. You can only do an expanded octet if you're on the third row or lower. So we've got carbon's got a combining capacity of 4, oxygen's got a combining capacity of 2, and hydrogen has a combining capacity of 1. So carbon will be in the middle. But TVS, carbon wants 8. Oxygen wants 8. This is total surrounding them, not how many more they want. And then we've got 2 hydrogens, and each one of them wants to have 2 around them. Valence electrons. Carbon brings 4, oxygen brings 6, and hydrogen brings 1. And there's 2 of them. So 8 and 8 is 16, and 4 is 20. 4 and 6 is 10, plus 2 is 12. So if we subtract 12 from 20, we get 8. If you divide that by 2, we know our structure has 4 bonds. And that makes sense because carbon will always make 4 bonds. So carbon, hydrogen, hydrogen, oxygen, 1, 2. Oxygen can make 2 bonds. There's our 4 bonds. So now, let's go back to the valence electrons. We have 12 to place. We've placed 8, 2 in each bond. So 12 minus 8 is 4. We have 4 electrons left to place. If we look at this structure, Hydrogen's happy, it's satisfied. Carbon is satisfied, and that comes through the bonding for carbon. What's not satisfied is oxygen. Currently, it only has 4 electrons. So those electrons go on oxygen. So now we have used 2, 4, 6, 8, 10, 12 electrons, which is all we had to start with. So there's our structure. If we do TVS, sorry, formal charges, not TVS, formal charges. We've got carbon, we've got oxygen, and we have hydrogen. Carbon has 4 valence electrons. It has no electrons in lone pairs, but it did make 4 bonds. So it's looking good. Oxygen, we have 6 valence electrons, 4 electrons in 2 lone pairs, 2 bonds, 0. And hydrogen. Hydrogen brings 1, has no electrons in lone pairs, 1 bond, 0. So, this is an awesome structure. It must be correct. Our formal charges are 0. Okay, if we have a Lewis structure where we have a polyatomic ion, we have to add electrons in order to satisfy our structure. So, nitrogen brings 5, 3 oxygens will bring 18, and a negative charge will bring 1. You should always end up here with an even number, because in a Lewis structure you either have bonding pairs or lone pairs, and of course pair means 2. So here we go. Nitrate. So nitrogen has the highest combining capacity of 3. Oxygens, there's 3 of them. So we've used 6. So we have 18 left to place. So what you have to do is you start by filling the octet of the outside or the terminal atoms. So each oxygen currently has 2 through the bond. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have no more electrons. We're done. We've placed 8, 16, 24 total. Each oxygen has its octet satisfied. However, nitrogen does not. It only has 6. It wants 8. However, we have no more left to place. So what you have to do is if you're short electrons on your central atom, you take a lone pair and you make a double bond. So the structure becomes put my dots back on for my electrons. So let's see. Oh, that's bad. There, let's move those down. Okay, so 8, 16, 24. I've only placed 24, but now everybody's octet is filled. So the only thing we have to do is put square brackets and a charge because it's an ion. Now, formal charges. Nitrogen. Now we have 2 different oxygens. We've got a double bonded oxygen and single bonded oxygens. So what we're going to do this one, the second one, by 2, because there's 2 of those. All right, nitrogen, 5 valence electrons. It has no lone pairs, and it made 4 bonds, so it is +1. Double bonded oxygen, so 6 valence electrons, and if we look at the double bonded one, it's got 4 electrons in lone pairs, and it made 2 bonds. So that number is 0. All right. Single bonded oxygens bring 6 valence electrons. They happen to have 6 electrons in lone pairs, and they each make 1 bond. So the formal charges on the single bonded oxygen is -1, but we're going to multiply this by 2. So the total here is -2. -2 and +1 is -1. So they add up to give you the charge on the ion. It would be better if we could have a formal charge of 0 on as many atoms as we can. So let's just take a look at what we would have to do that. Okay, if we want to get more formal charges to 0, what we usually end up doing is making more double bonds. So bear with me for a minute. So we're going to make 1 more double bond and do the formal charges. So just pretend for a minute. What we do when we do structures is we actually play a little bit with them to see which one gives us the best answer. So it's not always straight up. So nitrogen, formal charge, 5 valence electrons, no lone pairs, 5 bonds equals 0. So that's looking good. Double bonded oxygen. So 6 valence electrons, 4 electrons in lone pairs, 2 bonds, 0. Nice. Single bonded oxygen, 6 valence electrons, 6 electrons in lone pairs, 1 bond, -1. So this adds up to -1. But there's a big problem with this structure. We did manage to get our formal charges down. However, nitrogen is on the second row of the periodic table. It cannot expand its octet right now. It's surrounded by 2, 4, 6, 8, 10 electrons. Can't do it. Nitrogen is on the second row of the periodic table, so it has to be surrounded by 8. So this is not the correct structure. This is, but I just showed you how to reduce the formal charges so you have more that are 0. Sometimes we can do this, and I'm going to give you an example right now. So SO4 2-. Sulfur brings, I don't know why I just wrote a 2. Sulfur brings 6. 4 oxygens bring 6 each. And then there's a 2-, so you add that in as well. So 5 times 6 is 30, plus 2 is 32. So there's 32 electrons to place. So sulfur, oxygen, 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 oxygen. In terms of combining capacities, they happen to be the same for sulfur and oxygen, but there's 1 sulfur, 4 oxygens. Sulfur came first, put it in the middle. We also go with usually the least electronegative atom. Sulfur is less electronegative than oxygen. Okay, so we've just placed 8. So we have 24 left to place. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 2 minus. All right, so we've used 24 electrons to fill up our outside atoms octet, and total 8, 16, 24, 32, and everybody is surrounded by 8. So their octets are complete. You'd think they'd be happy. So formal charges. Sulfur, 6 valence electrons. No lone pairs. 4 bonds. Ooh, +2, not looking good. We don't like that. Oxygen, there's 4 single bonded oxygens. 6 minus 6 electrons in lone pairs, minus 1 bond, -1. But we have to multiply that by 4, because there's 4 of them. So 4 times -1 is -4, plus 2 adds up to -2, so that part is correct. However, we don't have any zeros. Formal charges really want to be 0 or as close to it as possible. So if we make a double bond, we can reduce a plus charge by 1. So if we make 2 double bonds, stands to reason we should be able to get the formal charge on sulfur down. So let's try this. Right, the last structure we drew for nitrate, we reduced the positive by 1 by adding a double bond. So let's do this. Formal charge is sulfur, double bonded oxygen, single bonded oxygen. Sulfur, 6, no lone pairs, 6 bonds. It's looking good. Double bonded oxygen, 6, 4 electrons in lone pairs, and then 2 bonds, 0. Looking even better. Single bonded oxygen, 6 valence electrons, 6 electrons in lone pairs, and 1 bond. And now we have to multiply this by 2 and this by 2 because there's 2 of those atoms present, so it adds up to -2. So this is actually the best structure for sulfate. Now, based on formal charges, that is, right? Based on formal charges, we've got more zeros, adds up to -2, so it's the best structure. If we look at sulfur, all the oxygens are surrounded by 8. Sulfur, however, is surrounded by 2, 4, 6, 8, 10, 12. 12 electrons. But it's on the 3rd row of the periodic table, so it can expand its octet. It can be surrounded by more than 8 electrons. And that's how you do those structures. Carbon dioxide. This is always a good one. Carbon brings 4, 2 oxygens bring a total of 12, 16 electrons total. Carbon has the highest combining capacity, so it goes in the middle. Put our bonds in. So I've used 4, leaves 12. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now oxygen's happy. Each one has 8, but I have used 8, 16 electrons. I only had 16, so I'm short. Well, I am short, but short on electrons. So, if you're short on electrons, make a double bond. This way, more electrons are shared. So, here we go. 2, 4, 6, 8, 10, 12, 14, 16. 16 used, 8, 8, and 8. Everybody's happy. Their octet has been satisfied. Now, let's do an unusual one. Let's do XeF2. So Xe, xenon, is a noble gas, but because it's big, it can actually be made to form bonds. So xenon will bring 8 valence electrons. 2 fluorines will bring 14. So we will have a total of 22 to place. So put on Xe, put on your bonds, and your other 2 atoms. Now, we've used 4, so we've got 18 left. Complete the octet for your terminal or outside atoms. 2, 4, 6, 12. We now have 6 electrons left. We've got 8, 16. We've got 6 more to place. Fluorine's happy, it's got its 8. Xenon will need 4 more to get 8, but there's actually 6 still to place, so if there's extra ones, you put them on the central atom. So xenon has an expanded octet because it is surrounded by 10 electrons. 2, 4, 6, 8, 10. And we have placed 8, 16, 17, 18, 19, 20, 21, 22. 22 electrons, and we had 2. So that, in a nutshell, is how we do with structures this year.